got an RS232 serial interface built for my 6502 breadboard computer. It can transmit to a serial terminal program, and if I type into the serial terminal, the 6502 computer receives what I type. The problem is that all of this is very CPU intensive. The serial port is communicating at 9600 bits per second, which means each bit takes 104 microseconds. And the way the computer receives data is it reads each bit from port A in a loop here. And for the timing to work, we had to ensure this loop takes exactly 104 microseconds. And since the processor is running on a 1 megahertz clock, each clock cycle is 1 microsecond. So all of this code to read a bit needs to take exactly 104 clock cycles. Now it doesn't, so we added this bit delay routine down here, which just has a do-nothing loop that loops 13 times and then returns. And we've also got some no-op instructions here that just do nothing, and all of this is carefully designed to take 104 microseconds per bit. But that means the computer isn't doing anything else useful while it's receiving data. Also, changing the baud rate from anything other than 9600 bits per second would be a bit of a project. So this is not how most computers read serial data. Typically what you do is handle all the actual bit-by-bit data transfer in specialized hardware like this Universal Asynchronous Receiver Transmitter, or UART. And that's what I'm going to do in this video, hook this UART up to the 6502 computer. And if you'd like to follow along and experiment on your own, this UART is included in my new serial interface kit for the 6502 computer. And in addition to that, of course, you can also get the 6502 computer kit and any other kits on my website as well. So check out eater.net/shop for more information. But anyway, if we look at the datasheet for this, this is the 6551. They call it the Asynchronous Communications Interface Adapter, or ACIA. It's sort of the 6502 universe name for a UART. But UART's maybe a more common or generic term for something that would implement a serial interface like this, so I may end up using those terms interchangeably in this video. But if we look at the description, it says it provides an easily implemented program-controlled interface between 8-bit microprocessor-based systems and serial communications equipment. And it says the transmitter baud rate can be selected under program control to be either one of 15 different rates, from 50 baud up to 19,200 baud, or you can customize it more to something else. And it'll handle transmitting 5, 6, 7, or 8-bit words. It'll handle parity, stop bits, and everything else. Then it talks about the different registers that it has for configuring and using it, but let's take a look at the hardware interface. Here's the pinout, and then they also have a basic block diagram down here of what's going on inside the chip. And the block diagram shows the same pins over here. So we've got, D0 through D7 are pins 18 through 25, and here's where they show that over here, pins 18 through 25. IRQB is pin 26, you can see pin 26 here, and so on. And actually a note about that, the B at the end of IRQB stands for bar. So you'd read this as IRQ bar, and that refers to the more common way this is represented, which is with a bar over the name. So for example, CS0 is chip select 0, and CS1B refers to chip select 1 bar. So you can see those are pins 2 and 3, and so this chip has 2 chip select signals. And in order to communicate with the rest of the computer at all, both of those signals have to be active. But chip select 0 is just a normal active high signal, whereas chip select 1 is an active low signified by the bar over it, or the B, I guess. So for the rest of the computer to be able to talk to this chip at all, chip select 0 has to be high, and chip select 1 has to be low. And I'll just point out that this datasheet doesn't actually explain this convention anywhere. This is just something you're expected to figure out, I guess. There's all sorts of conventions out there. You could have the bar over the name like this. You could have a little bubble here like this. You might have a little triangle thing here, however that goes, something like that. Or sometimes you'll see a slash in front of the name like this, which is easier to typeset, but I guess it's supposed to make it look like it was supposed to have a bar over the top, but then the bar kind of fell off. But anyway, so when you're reading a datasheet, it might not be obvious what notation they're using. But one clue is to look at the pin descriptions. For example, if we look at the pin descriptions for the chip select, it says the chip is selected when chip select 0 is high and chip select 1 is low. So that's a clue. But anyway, you can see that the rest of the pins on this side over here are for interfacing with the rest of the 6502 computer. And the pins on this side, for the most part, make up the RS232 serial interface. And right now I'm not planning to use most of these. Because the basic serial interface really only requires transmit data and receive data, of course ground. So I'll just start with those two. You can see transmit data here and receive data here, and this diagram kind of shows how it works. So when it receives those data bits, they get read and shifted into an internal receiver data register at the correct baud rate, which we can configure. Then when that whole byte will be sitting in that data register waiting to be read, all 8 bits at once by the computer on D0 through D7 as a single operation. Then the computer can go back to doing other stuff as more data is received. And for transmitting, again, the computer can put an entire byte into the transmitter data register as a single operation, then get back to doing other stuff, while this chip handles transmitting at 1 bit at a time using the correct timing and such. And the interesting part is, how does this interface with the data bus and the CPU and everything? But let's just start hooking it up and I'll get to that. So I'll add the 6551 UART here. Power is pin 15 and ground is pin 1. And I suppose I should power off the computer while I'm doing this. So let's start with this side here, the RS232 stuff, since we're actually not using most of it. But we are using transmit data and receive data, but we can't just hook the transmit and receive data coming in from our serial port directly into the UART. As I talked about in previous videos, RS232 uses a positive and negative 10 volt or so signaling, not the 0 and 5 volt logic signal. So we still have to use the MAX232 chip as a charge pump to convert the voltage levels. But instead of manipulating those signals directly via the universal interface adapter here, we'll hook the receive data out from the MAX232 to the receive data pin on the UART. And the transmit data pin on the UART goes to the transmit data in on the MAX232. So that's transmit data and receive data. We're not using ready to send or clear to send. We're not using data terminal ready or data set ready. We're not using data carrier detect or receive clock for the baud rate generator. But we do need to provide a crystal oscillator here on pins 6 and 7 for the baud rate clock generator. If we look at the description of those pins, it says they're normally directly connected to the external crystal to derive the various baud rates. You can also provide your own clock if you need some other weird baud rate. But if we just want to use the standard rate, we need to come up with a 1.8432 megahertz crystal. So I've got one of those here. It's included in the serial interface kit if you happen to get one of those from me. And then to hook it up, back here somewhere, they've got a schematic of how you're supposed to hook up the crystal. So it shows the crystal here across pins 6 and 7. And then in parallel with that is a 1 megohm resistor. And then on pin 6 here, there's a 30 picofarad capacitor going to ground. So let's put that 1 megohm resistor across pins 6 and 7. Then I'll wedge the crystal in here across pins 6 and 7. And finally from pin 6 to ground with that 30 picofarad capacitor. So that pretty much takes care of all the pins on this side that we're planning to use. So now the interesting part is how this communicates with the rest of the computer. So the 8 data lines here connect to the data bus of the computer. And it's the same data bus that connects the CPU to the ROM, to the RAM, to the versatile interface adapter, and everything that we've been using for I/O so far. So now we're adding this UART onto the data bus as well. And this is going to present some challenges because we need to make sure that when the CPU is using the data bus to talk to the UART, it's not going to interfere with the ROM or RAM or anything else. And of course, when it's talking to the ROM, RAM, or other I/O, we need to make sure it doesn't interfere with this new UART we're adding, because the nature of the data bus is that all these things are connected simultaneously, and you need some way of ensuring that at any given moment, only one thing is transmitting and only one thing is receiving on that data bus. So to simplify that, in this design, the CPU is always involved. So it's always the CPU transmitting to or receiving from one of these other devices. So that means if you have data in memory, let's say, and you want to send it out the serial port, even though the memory and UART are connected together through this data bus now we've added this data bus to the UART, it'll have to go through the CPU. The CPU would read a byte from memory into an internal register across the data bus, and then it would write that byte back out on the bus to the UART to get sent. Then the CPU would read from memory again to get the next byte, then write that next byte out on the data bus to the UART, and so on. And so perhaps you've heard of something called programmed I/O or PIO. That's what this is. There needs to be a program running on the CPU moving each byte of data from the I/O to the memory or vice versa. So a more efficient method, which would be much more complex, is direct memory access, where the I/O device, like the UART here, could directly pull data from memory or put data into memory as it sends and receives, without involving the CPU for each byte. So if you've heard of DMA or direct memory access, that's what that is. But for that to work, you've got to have some mechanism for bus arbitration, deciding and switching which of these different devices that's connected to the bus is the bus master. So bus master refers to whichever device gets to control the bus at any point in time. And bus arbitration is some sort of process for switching bus masters. But in the 6502 architecture, unless you do some weird stuff, the CPU is just always going to be the bus master. Though if you want to see me do some weird stuff, I did implement some kind of sketchy DMA when I attached a VGA interface to this, so you can check that out over there. But anyway, in this case, the CPU is going to control when the UART will access the data bus, and the way it's going to do that is using these control signals. Now, I mentioned chip select lines before, and the way they work is that unless chip select 0 is high and chip select 1 bar is low, the data lines here will effectively be disconnected from the bus. They'll be in a high impedance state. And so that's how the CPU can disconnect this entire chip from the rest of the bus. So what we need is some logic connected to those two pins, the chip select pins, that let the CPU indicate when it wants to talk to the UART. And the way the CPU generally indicates what it's talking to is using these address lines, these green wires. Because in addition to the 8 data bits that connect everything, there are 16 address bits that the CPU uses to pinpoint a particular address for the data that's on the data bus. So if it wants to talk to a particular device, there's some address that device will recognize on the address bus. So the CPU will put that address on the address bus and then put the data on the data bus, or put that address on the address bus and then read data from the data bus, expecting it to come from whatever device it's addressing. So let's look at how that works. Here's the address map of the computer, and it shows address bits A0 through A15. And if A15 is high, then that says the CPU is talking to the ROM, and then the rest of the address bits indicate where in ROM it's reading from. And you can see that on the schematic. So here's the CPU, and A0 through A15 are connected to this bus here, and then A0 through A14 are connected to the address lines on the ROM. But A15 is down here, and then it gets inverted. So if A15 is high, it gets inverted, it's low, and then it goes into the active low chip select for the ROM, which enables the ROM only when address 15 is high. And that has the effect that whenever the CPU is talking to an address where A15 is high, so that could be one, all zeros, or 8000 hex, through one, all ones, which is FFFF hex, any addresses in that range are ROM addresses. And if the CPU is talking to some other address where A15 is 0, then the ROM chip won't be active. Similarly for the RAM. In that case, A15 and A14 both have to be low, and then the rest of the address bits are used to, for the specific RAM address. And so if we take a look at the schematic, it's a little bit more complicated for the RAM chip because of some, timing stuff. You can check out one of my previous videos for details on that. But here's the RAM chip, and if address 15 is low, it gets inverted, then inverted again, and goes into the active low chip select for the RAM. Then address 14 actually goes into the active low output enable. So both address 14 and 15 have to be low in order to read from the RAM. And then the rest of the bits are used to figure out where in RAM. So that makes the RAM addresses 0000 through 3FFF. And then everything from 4000 through 8000 is kind of available for I/O. And right now the versatile interface adapter is active on the bus anytime A15, A14, and A13 are 011. And then the interface adapter has 4 address lines connected to it because it's got 16 registers in it to handle the various things it does. And those 4 address lines let you select whichever you want of those 16 registers. So if we look at how that works, you see address 15 is inverted, and then it gets ANDed with address 14. That gets inverted, and then that goes into the active low chip select 2. So that'll be active low when address 15 is 0 and address 14 is 1. Then chip select 1 is just connected directly to address 13. So the chip will be enabled whenever these address bits are 0, 1, 1. And then address 0 through address 3 are connected to the register select pins, and that's it. So these other bits here, address 4 through address 12 are never getting looked at. So if you assume they're all 0, then the address range is 6000 through 600F for those 16 registers in the VIA. Yeah, but these other bits could be anything. If we had 0111 and then the rest zeros, that would be a 7, followed by whatever. So 7000 through 700F would actually also, enable the VIA and access its 16 registers. So there's actually lots of different addresses you can use to talk to the VIA. But I've just been using 6000 through 600F, or at least that range. So where does our new UART fit into this? Well, it's actually pretty simple to add it at address 5000 because it's pretty simple to check if address 15 is 0, address 14 is 1, and then if address 12 is 1. So here's a new schematic where I added the 6551 UART, and it's connected to the MAX232. Here's the transmit and receive lines there. And the MAX232 has all its capacitors for the charge pump and is connected to the DE9 serial connector. But on the UART, I've got all the data lines here hooked up to the data bus, just like we did. And here's the crystal oscillator, resistor, and capacitor. But let's take a look at the chip select lines. So chip select 1 is active low, indicated by the bar over the top there. And that's connected on down to this logic here that's going to go low when address 15 is high. Or no, excuse me, when address 15 is low, because it gets inverted. And then when address 14 is high, then this goes low and goes into chip select 1, which is active low. So that's going to be active. But chip select 0 also needs to be active, and it's active high. So it's connected right here just to address 12. So address 12 has to be high, address 14 has to be high, and then address 15 has to be low. Then address 0 and 1 select which of the 4 registers we're talking to in the UART. And so address 0 and 1 are connected to register select 0 and register select 1. And so that means that the CPU can get to the 4 registers in the UART by talking to addresses 5000 through 5003. Or, like I said, if these bits in here had different values, then you could have other addresses that would also work. But you want to use caution, because if address 13 happened to be a 1, then that would also activate the VIA, right? 011. So this actually has to be a 0. And then same here, if address 12 were a 1, then that would activate the UART, so this has to be a 0. And that also happens to mean that any address that starts with 0111 is going to be trouble, because that would enable both of these chips at the same time. So any address of 7000 through 7FFF, you don't ever want to touch. We can't ever use these addresses for anything with this particular architecture. So, is that wasteful? Well, like many things in engineering, it's a trade-off. If we needed more addresses for more memory or I/O or something, then, maybe we should be careful not to waste any. But if we don't need those addresses, then the simplicity of the logic circuitry that we're able to do with this design is a good thing. Our entire address decoding is 3 NAND gates. So that's the upside of this particular design choice, is we can avoid much more complex address decoding logic this way. So let's hook this up. Chip select 1 is pin 3, and that comes from this signal up here, which is the output of that NAND gate that goes low when A15 is low and A14 is high. And then chip select 0 is pin 2, and that goes around to address 12, so that the UART won't be active unless address 12 is high as well. And then address 12 here is going to be pin 22 on the CPU. So let me get that hooked up here to the right pin. There we go. So this ensures that now when we're reading or writing from 5000, we'll be talking to this chip, or this chip will be active. But there are 4 different registers in that chip. So writing to 5000 will put data in the transmitter data register. Reading from 5000 will read data from the receiver data register. But there's another 3 registers, a status register, control register, and command register that we can read and write from. And so those addresses will be 5001, 5002, and 5003. So to tell it which of the 4 addresses we're using, we'll hook up these 2 register select lines. So register select 0 is pin 13, and that goes to address line 0. And register select 1 is pin 14, and that goes to address line 1. And it's getting a little bit tight in here. So we've got our register selects, our chip selects, and then we've got our read-write signal. And this is how the CPU says whether it's reading data from the data bus or writing data to the data bus. RWB might be better written as read/write bar. So it's either, if it's active high, then it's reading. If it's active low, it's writing. And this is from the perspective of the CPU. So if it's reading, it's pulling data out of one of these registers and putting it onto the data bus. If the CPU is writing, then the CPU is putting data onto the data bus and trying to write it into one of these registers. Well, not the receiver data register, but one of these other ones. Which one? Well, that's what the register select pins do. And so the CPU has a corresponding read-write pin here, which is pin 34. And that just goes directly to the read-write pin down here on pin 28 of the UART. And then finally, there's the timing and control. So Phi2 here refers to the system clock, which is this 1 megahertz oscillator right here. So we can just connect the output of that into pin 27. And the 6551 chip is specifically designed to work with the 6502 processor. So we don't really have to do anything complicated to get the bus timing to work. We just feed it the same clock, and the timing requirements are designed so it just works. And then lastly, we've got the reset pin. That's pin 4, and I'll connect it to our reset button here. So when we reset the rest of the computer, the 6551 is reset as well. And so that's all these pins here, except for the interrupt request pin. That would go to the IRQ line here on the CPU, but that's currently connected to the versatile interface adapter. And without a little extra logic, we can only have one of them directly connected. So I'll leave that alone for now. Perhaps we can hook it up later. And so that's pretty much everything we need to get the 6551 connected into our 6502 computer. Except that in looking over this and checking that everything was hooked up right, I realized that the data lines are completely backwards. So that definitely would have caused some problems. So let's try doing that again. So D0 is here. And then that's going to connect to D0 up here. And I think I had connected it over to D7 instead of D0 before. Then we'll hook D1 to D1, D2 to D2, and so on. And I'll try to make this somewhat tidy and get the rest of these hooked up the right way. And there we go. I'll tidy this up a little bit more. And I think with that, now we've got everything connected properly. Yeah, and this one certainly would have been a fun one to troubleshoot if I hadn't caught it earlier, because everything would have worked properly except the data and commands and everything that were being sent to the 6551, all the bits would be flipped around, so it just wouldn't behave properly. So I'm glad I caught that, because that could have led to a lot of head scratching. So with the hardware all hooked up, we've now got access to the 4 registers. The data register is at address 5000, and depending on whether we're reading or writing, we're either reading from the receiver data register or writing to the transmitter data register. And the data sheet explains that here, where it talks about the register select pins. So if both register selects are low, then it shows that we can write and read the transmit and receiver data registers. If the register selects are 0 and 1, that lets us read the status register. So I can define the status register at address 5001. Then if the register selects are 1, 0, that lets us read and write the command register. So the command register is going to be at address 5002. And finally, if the register selects are 1, 1, that lets us read and write the control register. So the control register is going to be at address 5003. And at this point, it's just a matter of loading a value into the A register and then storing it to one of these addresses. Or in order to read one of the registers, you can just load from one of the addresses into the A register. But I think at this point, I'm going to save all that for the next video, since there's actually a whole bunch of different options to explore here. But if you're following along with these videos in real time, I'd encourage you to hook all this up and then take a look at the datasheet where it describes the different registers and give it a try yourself. And, if you get stuck, I'll be back in a few weeks with a new video where I'll hopefully have something working. But in the meantime, I definitely recommend giving it a try. And as always, you can get schematics, data sheets, and kits and everything on my website, eater.net/6502. And of course, thanks to all my patrons who are a big help in making these videos possible. So thanks again.